Hello everyone, and welcome back to another video. So I've been noticing lately that a lot of my students have been struggling with balancing and predicting the products of chemical equations. Not sure why this is. In most years, this is not a particularly hard topic, but I figured I would go into it anyway. So what I've done is I created this flowchart, which should help you decide which type of reaction you're looking at and then predict the products relatively easily. And I'm going to try using an exam question from probably the hardest chemistry class in the US, which is the one here at Cornell. So let's get into it. As we look at our first question here, C4H10 plus O2. The first question in this flowchart is always how many reactants do we have? And here we've got 2. So next we'll ask ourselves, what are they? In this case, they follow the form CXHY plus O2, which tells us definitively that this is going to be a combustion reaction, which is a subtype of redox, which means the oxidation states are going to change from products to reactants. Now, the nice thing here in combustion is that the products are always the same. They're just H2O and CO2. And the only real challenge here is to balance the reaction. The method I prefer to use is to add a 2 before each of the reactants. What this does is it creates an even number of oxygens, specifically by doubling the number of oxygens in water, which makes balancing a lot easier because we have an O2 on the left side, so we've got to have an even number of oxygens. First, I will balance the carbons. So 2 times 4, that's 8. We need to put an 8 in front of the CO2. Then let's see what that does to the oxygens. Okay, so 8 times 2, that's 16. And then we've got 2 times 1 in the water. That's 18, so we'll put a 9 in front of the O2 to balance that out. We've got 2 times 10 hydrogens on the left side, that's 20. So we'll have to add a 10 in front of the water on the right side. But that's going to affect our oxygens, so we have to recalculate. Now we've got 26 oxygens on the right side, so we'll put a 13 in front of the O2 on the left side, and we're good. All right, moving on. So here again, HNO3 plus CrO3. We've got 2 reactants again, but they've got a different format this time. Here we have a metal and a non-metal in H and nitrate because we consider polyatomics as non-metals. And then other reactants the same. It's chromate, metal, plus oxygen, non-metal. What that tells us is that we've got a double replacement going on here, where we're going to have to switch the 2 metals to find the products, and then decide from there what to do next. So here we'll flip H and Cr, and here I like to leave things as separate ions until I figure out all of the ratios, because the charges will tell us what the ratios are, and we're not sure of all the charges yet. So Cr will get a question mark, but we do know that NO3 is a 1- polyatomic, so we can put a minus sign there. And then we'll combine H, which is 1+ because it was paired with the 1-, and O, which is always going to be 2- as an ion. Now, here comes our next decision step. We know that when we combine H and O, we're going to get water. That's pretty much always the case. And since we produce water here, that means this is going to be an acid-base reaction. And to figure out the ratio between chromate and nitrate, we can look at the number of negative charges in CrO3. So O is always 2-. There's 3 of them, that's 6-, so chromate must have been 6+ to balance it out. So we'll keep that charge because this is not redox, it's acid-base, which means that we'll need 6 nitrates to cover the 6+ from the chromate, leaving us with Cr and O3, 6. Now to balance, we'll start with the nitrates. There's 6 on the right side, so we'll put a 6 in front of H and a 3 on the left side. That gives us 6 H's, which we can balance by putting a 3 in front of water. And that gives us 3 O's on the right side, but conveniently we've already got 3 O's on the left side, so we're good. Okay, next one. So same format, 2 products, metal, non-metal, metal, non-metal. We're gonna have that same double replacement technique where we switch H, barium in this case. So H combining with OH, that's always gonna make water. So that's one of our products, meaning this is also going to be acid-base. And then to figure out the charges for barium and phosphate, OH is a 1-, and there's 2 of them. So that means that barium's got to be 2+ to balance that. And H is 1+, and there's 3 of them, which means that phosphate has to be 3-. So when we combine this, Ba2+ and PO4 3-, so we get Ba3, PO4 2. It's like we just switch the charges. So to balance here, we'll start with putting a 3 in front of the BaOH2 compound to balance the 3 bariums from the right side. That will give us 6 OHs, that's 3 times 2. So we'll need to put a 6 in front of water, which gives us 6 H's additionally. So we'll need to put a 2 in front of H3PO4 to get 6 H's there. And that conveniently also gives us 2 PO4s, which balances the whole thing out. Okay, this looks a bit different. So here we've only got one reactant and it's being added to heat. So on our flowchart here, that means we're looking at a decomposition reaction, which is a type of redox. And the strategy that I always use here is to look within the reactant for things you already know. So what I mean by that is we're gonna look at N just by itself. What's a compound that you know that just contains N and is ideally a gas, because decomposition usually makes gases? If you guessed N2, that makes sense. That's the only compound that exists that just contains N. And we do the same thing for I. So what's a compound that just contains I and is ideally a gas? Here again, we're thinking about I2. So our products here are just going to be N2 gas and I2 gas. Balancing is relatively simple. We can just put a 2 in front of Ni3 to balance nitrogens, and then that will give us 6 I's, so we'll put a 3 in front of I2. Okay, NiO plus Al. 2 products, but here it's in the format metal nonmetal plus metal. That will give us what's called a single replacement reaction, which is also a redox subtype. The procedure, simple. We're just going to switch the metals. So we'll end up producing some compound with Al and O, and then nickel alone. I said some compound with Al and O because we don't have the ratio yet. It may not be this 1-to-1 ratio that we have with NiO here. To figure that out, we've got to think about the charges on each of them. So O is 2 minus, Al is 3 plus. So to form a neutral compound between Al and O, we need to actually make Al2, because 2 times 3 plus is 6, O3, because negative 2 times 3 is negative 6. Then to balance here, we'll put a 3 in front of NiO to balance the oxygens, then a 3 in front of nickel alone to balance itself, and then 2 in front of Al to balance the Als and Al2O3. This look pretty familiar by now. We've got another double replacement here with metals and nonmetals, so we'll switch the Cu and the K. So we know that because Cl is always 1 minus, Cu is going to be 2 plus, and we know that because the K is always 1 plus and there's 2 of them, that CO3 should have a 2 minus charge. And then we can just combine K and Cl. We know they've both got 1 plus and 1 minus charges respectively. And balancing here is really simple. We've got 2 Ks and 2 Cls in the reactants, so we'll just put a 2 in front of KCl on the products, and the Cu and the CO3 don't need to be touched. However, when we are working with double replacement reactions that are not acid-base, we do have to check for a precipitate, which is here on the flowchart, because there's no water produced. KCl, we should know that K plus is group 1 metal, which means it's always soluble. But in CuCO3, carbonate is pretty much always insoluble, so that's going to be a precipitate here, which makes this a precipitation reaction.